Okay, test. People are joining online. Can you type a yes? You can hear me? Thank you. All right, let's start it. Fourier series. So this is what we covered at the end of the previous lecture. Essentially, we talked about a new concept, and this is the concept of approximation concept. We learned, actually in first year, you learned a concept called series. You know, the different series you learned, Maclaurin series, there's Taylor series, right? So Fourier series technically is just a case falling into that first year, right? Now, of course, Fourier series has its own focus. It focuses only on functions with a period of a t naught, or it applies only to periodic function. And if you have a periodic function, then this function can be decomposed into a number of terms associated with the cosine and sines. And of course, each one of sine, cosine has a different amplitude, also has a different frequency. But the frequency are multiple of each other. So that's essentially what Fourier series is all about. A periodic function is being decomposed into an additions of sines and cosines of the different amplitude and the different frequencies. We give some of the names to some of the coefficients here in the formula. So we call, for example, A naught as a DC component, because apparently this is a constant, and the other terms are all associated with sine, cosine. So we call the rest of the term as AC components. And also remember, T naught is a period, omega naught is a frequency, fundamental frequency. So the relationship, right, is omega naught equal to 2 pi over T naught. As you can see in the formula, the rest of the terms are all just a multiple of this omega naught, or the fundamental frequency. So that's why sometimes we call this as a harmonic motion. Right? So when you have a harmonic motion basically means it consists of a fundamental frequency and then plus some other frequencies that are multiple of the fundamental frequency. The formula for calculating A naughts, AN and BN are listed over here. They are not really any difficult. So they're basically integrations, okay, simple integrations. F of t is your original periodic function. You're integrating just within one period, 0 to T naught. Right? So there's no, technically there's no difference from any integrals that you have conducted like for your first year. So one of the example we started. We're looking at the periodic function. So there's a whole bunch of boxes, right, and repeating itself. So it's a periodic function. Now, as I mentioned, one of the very, very fundamental skill that you need to have is if you're being presented with a periodic graph, okay, or periodic function graphed in here, then you have to be able to identify what is the period. Okay. So you can start anywhere in the graph, and you go in the positive t-axis direction, okay, and until it starts to repeat itself. So that amount of time you go through is the period. So in this case, period t naught is 2, and then omega naught would be just simply 2 pi over t naught, which is pi. So pi, of course, omega naught is reading per second, right? So let's suppose this is a second. Okay. All right, so now then we calculate each one of the constants A naught, AN, and BN according to the formulas given in here. Now, A naught, often in time, you could identify A naught without even calculating this using the formula. Okay. So A naught we said is a DC component, right? So DC component refer to basically the average value, okay, based on this graph. And this graph based on this, sorry, this is 1 here, and average value for this always is 1/2. So you could simply just write it as 1, but of course, for safety, if you're not too sure, you can certainly calculate this A naughts using the formula. So here's the formula for calculating A naught, and T naught is already identified as 2, and f of t, right? You're integrating from 0 to 2. So basically, you look at the graph, you're integrating from here to here, right? So within this range, you have f of t only exists between 0 and 1. So your integral technically is only integrated from 0 to 1. And within 0 to 1, the value of the function is 1. Overall, you get 1/2. And that's exactly the same as your observation based on the graph of DC component. That's A naught. So let's take a look at AN and BN. Now, A and BN, unfortunately, you probably won't be able to just observe and then write down the result. So you're going to have to do some integrals. Formula, write down the formula first. And by the way, you will have the formula, so you don't have to worry about it. But I always recommend that you write the formula a few times yourself, just to become friends with the formula. Here's the formula for AN. Same thing. So let's plug in T naught first, and also plug in the omega naught. So 2/2, 0 to 2, f of t cosine n pi t dt. So far, so good. And now, again, you're integrating within one period 0 to 2. So same as the previous example, from 0 to 2, the f of t exists only between 0 and 1. And the value of that is 1. So when you look at this integral here, 2 to 2 is 1 now. So you only integrate from 0 to 1. And the f of t will be 1 within that range. And you're left with just n pi t dt. So you're essentially just integrating a cosine n pi t now. And of course, n equal to 1 and 2, and that's by default, right, what n numbers is. So then what is the integral of a cosine n pi t? Well, that's simple integral. You get 1/n pi, and then sine n pi t. Right, so the result of the integral is 1/n pi sine n pi t. Then you substitute the t's range from 0 to 1. It seems there are a lot, sometimes people are scared of with all the symbols, but it's simple, right? So just focus on what you're doing. You're integrating with respect to t. Okay. N is some kind of constant from 1 to 2 to infinite. Once you plug in 0, 1 into the sine, and this is where you need to have some common knowledge about sine value or cosine value at some integer pi numbers, or even half of the pi, or 3 pi over 2. Okay. So when you plug in 1 over here, you got n pi, and sine n pi doesn't matter what n is, right? Sine n pi always is 0, right? And you plug in 0 here, sine 0, of course, is also 0. So the whole thing equal to 0. So I always say, you need to be able to draw sine t at least. So you plug in, even you plug in different n numbers, you look at the sine t, and you'll be able to identify what the value is if you can't remember it, right? So as an engineering student, I think some of these very basics, this is called a basics, you should be able to do without plugging it into your calculator. Okay, so an, right, is always 0. An does not exist for this periodic function. That's good. So now let's calculate Bn. This is the formula for Bn. Same treatment, plugging the T naught and plugging the omega naught. So you get 0 to 2 f of t sine n pi t dt. And we only integrate between 0 and 1 due to the nature of f of t. Now you're only integrating sine n pi t from 0 to 1. The result of a sine integral is cosine. Technically negative, so put a negative in front of it. And then 0 to 1 is the limit. Plugging the limits into the cosine. So we get 1 over n pi. Once you don't forget the negative in front of it. And you want to plug in 0 to 1 into the limit. When you plug in 1 here, now you get cosine n pi. When you plug in 0 here, you get cosine 0. Cosine 0 is 1, right? So you get 1 minus cosine n pi for this integral result. So I left the cosine n pi for here now. So this because it's not a simple 0 or 1 for cosine n pi. And that's, again, you have to be able to know some of the very fundamentals about cosine, right? So this is cosine t. If you have a cosine t, this is how it looks like. Pi over 2 here, and then you got a pi here. You got 2 pi here, right? Yeah. So basically, when you have a cosine pi, okay, when you got cosine pi here, the value is -1, right? And when you get a cosine 2 pi, the value is 1. So remember what the n is, right? Remember n is 1 to 2 to 3. Okay, that's your n value. So when you plug in n equal to 1, you get cosine pi, and cosine pi is -1. When you plug in n equal to 2 over here, you get cosine 2 pi, which is 1. And then you plug in 3 here, and you get -1. So this term, as n goes from 1 to 2 to 3, what does it do? It's oscillating between -1 and 1, right? And the oscillation between -1 and 1 depends on the value of n. Then this term, and you can clearly see, you can write it as -1 to the power of n. Right? When n equal to 1, -1. When n equal to 2, you got 1. So that cosine n pi can be simplified to be -1 to the power of n. And then you can write n, right, equal to 1, 2, 3, up to infinite. Good. Yeah. And often in time, we can simplify this a little bit more. Okay, wouldn't call it simplified, but maybe just a little more informative. Okay, if you write one more step, essentially, if you look at if n is an odd number, so 1, 3, 5, 7, 9, right? Those are odd numbers. If n is odd number, and this -1 at here becomes negative. N is not number, -1 to the power of odd number is -1. So 1 minus -1 is 2, right? So you get 2 over n pi. So when n is not odd number, the Bn, so this is your Bn, is 2 over n pi. And when n is an even number, this is just become a 1. So 1 minus 1, 0. So your Bn will simply become 0. Okay. All right, so this is the results of Bn. As you can clearly see, I mean, to be honest, when you initially learn this, I can completely understand. You look at everything here, there's so many symbols throwing at you, right? But when you come down, you look at details, and nothing is tricky at all. Okay? Just a little bit careful. So now I got all of the constant value, and I can write my f of t using the formula for Fourier series. So that equal to 1/2, and then n. Okay. Originally, okay, if you look at the original formula, okay, so n start from 1 to infinite. Start from 1 to infinite. But however, we have just demonstrated that an is always 0, okay? And Bn exists only when n is odd number. So when you write this as a general format, you can start with n equal to 1, but then you can add 1, see n is just odd number, right? When n is even, it actually does not exist. So you can see n equal to odd and up to infinite. Then what is Bn when n is odd? It's 2 over n pi multiplied by sine n pi t. Okay. There's no an. There's only one term here within this summation sign. That's the result for f of t. If you wanted to write everything, write all the terms out, okay, instead of using the summation sign, so you can write it as 1/2 is the first term, and the second term is 2 over pi, and that's when n equal to 1, sine pi t, and the next term is when n equal to, what's the next term? N equal to what? 3, exactly. So 2 over 3 pi sine 3 pi t. The next one is 2 over 5 pi and sine 5 pi t. Right, so on and so forth. You can keep writing. So this might be, to some people, more acceptable than a summation. So people can clearly see, oh, look, f of t is a summation of, and this whole bunch of sine terms, sinusoidal signals. Okay, yeah. So this is mathematically how to compute the Fourier series of a periodic function. Okay. So I haven't really give you a little bit more meaningful explanation or interpretation yet. So I'll show you something. But so far, if you reflect on what we have done for a periodic function, how do I write it into a summation of all the sine and cosine terms? Right? You have three simple formulas, 3 simple integrals to calculate. And once you've done the calculation, and you can write f of t, right, using this Fourier series formula. Okay. Now let's examine this result here a little bit. Yes, very good. Okay. Okay, yeah. Absolutely, yeah. So let's examine these results a little bit here, okay? Yeah. First let's look at each one of the term. If I look at each one of the term, and can you tell me what is the frequency for the first sine? What is the frequency for the first sine term? So I'll give you a sine pi t. Let me ask you a question. What's the frequency of this? Anybody? You want to remember? pi. Exactly, right? So what's a period? 2 pi over omega 2, right? That's a period. So the first term here, look, the first term here, omega naught equal to pi. Okay, that's your frequency, and T naught equal to 2. So the first term, technically, if you go back to your periodic function, go back to this periodic function, what is the period for this periodic function? What is the period of this function? Go back to this question. 2. And what is the frequency of the periodic function? Pi. So the first sine term here, has exactly the same, what we call that, the fundamental frequency. Right? So this sine term, the first term here, and this has the fundamental frequency, omega naught. Is that good? Yeah. And if I plot this using any software, so you get essentially a sine curve, right? According to the first term. And then the magnitude is 2 over pi. Is that clear with the first term? Yeah. Now, second term, now basically, I'm going to illustrate just a few of them. And the second term, what is the, let's just write, maybe not, just write omega equal to pi equal to omega naught. This one equal to T naught, like this. Okay. What is the second term's of frequency? 3 pi, right? And its period, of course, you can calculate. And 3 pi is 3 multiple of your fundamental frequency. Is that good? Yeah. And magnitude is, the amplitude here is 2 over 3 pi. This question or no? Okay. This is 2 over 3 pi. In this case, 2 over 3 pi, do you think it's bigger than 2 over pi or smaller than is smaller, right? So if I draw a sinusoidal curve for the second term here, it start here, and now because frequency is higher now, and if this is your first one, so technically it becomes higher frequency, and the drawing is not very accurate. The magnitude here, the amplitude here should be shorter than the first sine curve. That makes sense? Yeah. And the third one, your frequency is 5 pi, which is 5 omega naught. And magnitude or amplitude is 2 over 5 pi. Again, it's getting a little bit shorter again, right? Than amplitude. So now if you plot it, it's getting a little more crowded or more frequent, and also the amplitude will get a little more shorter. Okay. So this is basically the trend for this one, right? You will observe. Each one of the term has a frequency of a multiple of the fundamental frequency. And each one of the term has an amplitude associated with it. In this question, the amplitude of each term actually is getting smaller. Okay, yeah. But what we obtained essentially, we're adding them up, right? We're adding all of these sine curves up. And then you end up with your original periodic function. Okay, so basically, if I show you if I draw the graph out, so here's a more of a what we're doing here. The red one is just the first term. Okay, the red one just the first term, and then the green and the what's the color, purple or blue, okay, are the number of terms n when you take as 5 and 20. So meaning, so for example, right? If I take this is 1, 2, 3, and then put 2 more terms behind this, that's basically when n equal to 5. You're taking 5 terms, okay? Or you take 20 of terms, right? So keep writing that here. And then you put them together, you add them together. So as you can clearly see that when n is 20, the green one is becoming more and more close to your original periodic function, which is a box. Does that make sense? Right. So basically, the first observation now you can see is that periodic function, which is a box, technically behind the box, behind the periodic boxes, okay, what's going on there? All the different sinusoidal curves. But you don't see that, right? Until you do this Fourier series, and you see that. And it's not arbitrary Fourier series, sinusoidal curve. It's curves associated with the fundamental frequency of this periodic function. So that's basically what Fourier series is all about. It tells you a periodic function consists of infinite number of sine and cosine terms that's associated with the fundamental frequency of your original periodic function. Okay. And also you can also kind of in your head, now because the magnitude in this case, the amplitude is actually decreasing. So the contribution of each one of the term, they're not quite equal. Of course, this term has the highest amplitude. So this term compared to contributions compared to the other term is probably more significant than the others. Okay. So here's a website I want you to explore a little bit here. It's called FALSTAD. It's in the lecture notes. Okay. Now, in this question, our fundamental frequency omega naught equal to pi, right? Equal to pi, and pi is only 3.14, right? So let's say, suppose that the omega. Right? Suppose omega, right? If omega equal to a different frequency, so let's say 622, this is in hertz. So let's say F naught equal to 622 hertz. Okay? And you can calculate omega naught based on hertz. Hertz is 1/T naught, right? That's give you a hertz. Okay. Now 262 hertz is the in the piano is the frequency of the C note. Okay, so suppose your omega naught is this, then technically what I end up with is a whole bunch of sine, and that are multiple of this fundamental frequency 262 hertz, which is middle C, right? Then you can try it out. Okay, so you can change the frequency over here. You can change to any frequency you want. So let's change to 262. Okay. That's not very accurate, but that's okay. And then this is the periodic function. Okay. Here you can choose a number of terms. If you just choose one term, and that basically just this one term over here, right? If you just choose one term, you can click on the sound. If you go to your piano, you press the central, the C note. That's exactly the C note, basically. Okay, yeah. Now, if you, if you give it a little more term, let's say 3 terms. If I have a 3, actually this is 3 terms, but the second term is 0. So if I write exactly the same, so 1, 2, 3. So that's the 3 terms that I have written down at here, right? The amplitude, you can see 1, 2, 3 amplitude. They are dropping in here, just like what we have predicted. Okay. Now this time, when you click on the sound, what would you expect? You have a C note, okay, the major C, and then you have another 2 sounds that's a multiple of the C note. So this is called, sorry about that, that's called harmonic, basically. Right? That's called harmonic. So you have a harmonic sound synthesized together. That makes sense? So in the future, basically, you can actually think of every periodic function. It consists of a different sound behind it, but you can't hear it. Yes. Sorry. Okay. I wouldn't say an octave because in piano, octave is like from C to what? To B. It's from 262 to 494, right? That's 1 octave frequency difference. But here, from pi, in this case, from pi to 3 pi. But in this case, if instead of pi is 262, then the next frequency is what? 3 times 262. That's right. It's higher. Yes. Yeah. Higher frequency. Yes. Yeah, you're right. So I think you can see it's one. I mean, not 1 octave. It's like 3 octaves, right? Yes. Does that make sense? So there are other interpretations, okay, but this is the one simple interpretation for a Fourier series. Okay. You can literally just consider a periodic function as a combination of a different sounds. Nice. The frequency, of course, could be rather than 262 hertz. Okay. The other information that later we're going to also tell you is, if you look at the graph over here, you can, this is a really good website. It shows you the term shows the sine, the term shows your cosine. So apparently there's no term shows cosine, right? That's exactly the same calculation what we did. You could also check mark here, it's called the magnitude and phase view. So magnitude is the magnitude as we have shown here. So this is the magnitude associated with each frequency of the sinusoidal curve. Okay. Yeah. Now phase, I'm going to come to that next. Just check out this website here. It's very intuitive. And you can also click on a different periodic function. So what I chose a square. You can also choose on a sawtooth. So basically like a ramp signal. As a matter of fact, one of the tutorial questions for next week. So we do have a tutorial next week. I'll post it. Of course, we only have tutorial from Monday to Wednesday. When you have a sawtooth, and how do you obtain its Fourier series? And same procedure, and you get a whole bunch of basically curves, like sine curves. Same thing. You can also click on sine. Okay. So here's actually a good question for you. You look at this sine here, right? Let's see if I give you a sine. If I give you a periodic function, let's say sine pi t. Okay. Here's a periodic function. What is its Fourier series? What would be its Fourier series? So if I write, this is a periodic function. If I write it into A naught plus, that format over there, and what do you think this side would be? 0? It can't be 0. I mean, you have sine pi t here, right? What do you think it will be on the right side? You don't need to calculate at all. Sine pi t, exactly. So the Fourier series of the sine pi t, sine pi t. Because why? How many frequencies exist in the sine pi t in the original periodic function? Only one, right? Omega is pi. And this is actually what you see. You see here, right? It doesn't matter how many terms you give. You only have one frequency exists at the fundamental frequency for a sinusoidal curve. Okay. And of course, if you click on the general noise, there's so many frequencies. As you can clearly see, you give, doesn't matter how many terms you give, you have an infinite number of terms exist. And that's because noise consists of the whole frequency spectrum from 0 to infinite, right? That's the idea. Okay. Any questions on the Fourier series? Okay. So to be honest, I think, in my opinion, the calculation Fourier series is not that difficult because you have the formula, right? And you can clearly calculate the Fourier series using the formula as long as you're comfortable with doing integrals. Okay. To check whether the Fourier series give you back the original f of t or not. You can, but I wouldn't recommend because technically you only get a very accurate approximation when you have an infinite number of terms, right? So I mean, if you only write down 3 terms, you plug in t to your right side, you get, let's say, for example, your left side is supposed to be 1, you're probably going to get a 0.8, right? Mm-hmm. You mean at some special locations of t? It could be, yeah. I mean, if you, for example, if you look at this graph here, so maybe at the t equal to 1, and then you actually, sorry to say, at the t equal to 1, you may actually end up at this location, right? So yeah, you know, you had to test it depending on f of t. Maybe at a very special t value, you got to accurate left and right. Yeah. Okay. All right. So let's continue from here just a little bit. Okay. And I'm not going to change anything, but I'm going to rewrite this Fourier series in a little more compact format. So essentially, we're going to use an identity. So you look at the Fourier series formula. On the right side, you have an cosine n naught t plus bn sine n naught t. So you have this on the right side as part of the formula for the Fourier series. Now, I want you to look at this lecture notes in lecture 30, in lecture 21. In lecture 21, I have presented actually, if you have an addition of a sine, cosine with same frequency, but could be different amplitude, this is an, okay, could be different amplitude, then you can write these two terms as one single term. It becomes Cn cosine n omega naught t minus a phase angle phi. So this makes it a little bit more compact. And Cn, okay, Cn equal to the square root an squared plus bn squared. That's your Cn value. The phi angle equal to the inverse tan bn over an. That's the phase angle. Okay. So then your f of t, right, can be written as C naught plus this summation sign n from 1 to infinite Cn cosine n omega naught t minus phi. C naught basically is the A naught from the previous formula. So this format here is what I call a compact Fourier series. A little more compact. Why is this good? The reason this compact one here actually specifically give us the amplitude and also the phase associated with this Fourier series. So let's see for example, right? From the previous example, okay? From previous example, we got our an equal to 0 and bn equal to that either 2 over n pi or 0. Okay. Then let's see what we're gonna get if we using this compact form. Okay, so Cn equal to an squared plus bn squared. And that equal to absolute value of bn. So Cn needs to be a positive number. So that gives us basically this is your bn, 2 over n pi, n equal to odd, 0 when n equal to even. That's your Cn value, which is essentially bn. Okay. And then the phi n, okay, the magnitude, not phi n, phi, the phase, right? The phase set here is tan inverse bn over an. And an is 0, it's always 0. So you got a non-zero divided by 0. Okay. Anything divided by 0 is infinite. So when you have a tan theta that equal to infinite, the theta got to be 90 degrees. So pi over 2. So this pi over 2 is associated with the odd when n is odd here. Okay. And that's it. That's your amplitude and that's your phase. So often in time, if we plot Cn, right, you can look at the Cn and versus the n and versus omega, okay, and you get, if you plot the Cn versus omega, then you get the so-called amplitude spectrum. And if you plot phi versus omega, and you get so-called phase spectrum. So these two information, you absolutely cannot tell if you just look at the time, you look at the function time domain. But if you do the Fourier series, and you will be able to get this very important information for behind this time domain signal. So as you can clearly see from the demonstration and here, when you have a square, so that's your amplitude spectrum plot, amplitude spectrum plot, and then the bottom here is your phase. As you can see, the phase, right? They did write it as a negative because this is actually slightly different square. This is a square symmetric to the t-axis, okay? And my square here is a square actually on top of the t-axis, right? So this is the t squared. Okay. So the phase is, in this case, the phase is pi over 2, in my case. Okay, so that's the compact Fourier series format. Right, so look at the lecture notes. There's one more example, so that can help you understand a little more on how to do this. Okay. So overall, so far until here, I probably don't have time to go a little bit deeper to the next topic. So we have what we have done. Okay, so to jog your mind here, we have done the so-called trigonometric Fourier series. Okay, Fourier trigonometric. So as you see, the final result is all in terms of trig functions, sine and cosine, right? And next, where we actually the next lecture we're going to learn is complex form of Fourier series. And then from here, it will lead us to the last topic, which is a Fourier transform. Hopefully I can I'll finish everything within one lecture in Monday, and then Thursday. And Wednesday, then I can use some time to do some final review. All right. Now, of course, if you want to relax from here to here, we're not going to test on from here to here. Okay, we're not going to test in the final exam, so it's more of just for your future. Because if you're going to electrical, you will learn this again. Okay, or you will be reviewed again. If you go into mechanical, I think you will too, because there is a vibration course. Okay, for civil, I'm not sure, but at least you will know, Fourier series, frequency concept. Okay, yeah. Okay, so any questions? I'll stop here a little bit early today. Okay. Okay. Excellent.